Hi, my name is Grady Cortez, and this is Lab 3, Black Hole. Introduction to this lab. The purpose of this lab is to deduce the mass of a black hole using the orbit of a star and to utilize this mass to find the necessary initial velocity for a spaceship to fly around the black hole after taking off from a nearby planet. We're using Newton's second law of the momentum principle, and we're also using the parallel and perpendicular components of net force and momentum. Important equations for this lab are the velocity update formula, Vf equals Vi plus F net over m times delta t, the position update formula, Xf equals Xi plus Vx times delta t, and the universal law of gravitation, negative g times mass 1 times mass 2, all over r squared times r hat. So the main results of the coding for both parts of this lab are the black hole mass is 3.87759 E plus 36 kilograms. F net was found to be 7.723 E plus 28 newtons. F net parallel was 2.21577 E plus 28 newtons. F net perpendicular was 7.40944 E plus 28 newtons. The found initial velocity vector was negative 1.3 E plus 8, 9.5 E plus 70 meters per second. And in part 2, we ended 4.1793 or 913 E plus 9 meters away from the event horizon of the black hole. And all the models, assumptions, and physics principles mentioned are used to prove that the momentum principle holds true and that it can be recreated in different settings. F net equals delta P over delta T. So the initial conditions for part 2, the system is a spaceship, the surroundings of the black hole and the planet. The initial conditions of the spaceship starts at T equals 0, at 1e plus 10, 2e plus 8, 0 meters, initial velocity of negative 1.3 plus 8, 9.5e plus 7, 0 meters per second, which is found. The mass of the spaceship is 7e plus 10 kilograms. Mass of the planet is 9e plus 28 kilograms. The mass of the black hole is 3.87759 E plus 36 kilograms, and G is 6.7 E negative 11. So for the first part of the coding, we use the mass of the star and delta T, which is the number of seconds in a day, to calculate the initial and final velocity, the initial final momentum, delta V, delta P, F net is dP over dt, F net parallel and F net perpendicular, and finally solve for the black hole mass by taking the average of the masses found via the glow script results. As you can see on the right, the main parts of the glow script results, as well as the diagram at the end, is shown to the right. For the second part, we use the mass of the black hole found in part 1, the estimated initial velocity vector, which was solved at the end, the planet's orbital speed of 1.611883 E plus 8 meters per second, and the planet's orbital period 0.108283 hours. And all this is a lot to explain. However, it's the distance vector for each place, and then you find the force on each place, and you calculate F net. So in the end, we were able to calculate F net on the spaceship, F net on the planet, and updating the planet's velocity, updating the position of the planet, updating the spaceship's velocity, updating the position of the spaceship, in order to solve for the initial velocity that can take the spaceship as close as possible to the planet, which is the estimated initial velocity vector above. And to the right again are the results via glow scripts. As you can see, the spaceship orbited around the planet, and also the code to the right. So comparison of the results, the mass of the black hole was the same value for both sections of coding, and the second part was able to utilize this to find an initial velocity of the spaceship that worked only with that found mass of the black hole. Different, the first code section only focused on finding the mass of the black hole, and the second section focused on finding multiple sources of force affecting the spaceship and utilized all those found values to find the initial velocity of the spaceship. This resulted in 2 different diagrams of motion around the same black hole, which are shown to the right. So some possible sources of error are rounding errors in the code, could potentially throw out the calculated mass of the black hole, as well as the initial velocity necessary for the spaceship to avoid the black hole and not crash into the planet. The initial velocity predicted could be off due to the value being determined based off trial and error. And p-hat used to calculate F net parallel in the first part was determined based on the initial momentum of the star. What does it mean for part 1? The net force and its parallel and perpendicular components are equivalent to the rate of change of momentum in its parallel and perpendicular components. Mathematically, they're the same. And in part 1, we actually used the star's momentum and change of momentum to find the gravitational force between the star and the black hole. Lastly, to orbit around the black hole completely, the initial velocity needs to be slightly greater than the initial velocity found. In part 2, the spaceship already almost orbits the black hole at this speed. and increasing the exponent to almost changing directions will have the spaceship orbit completely around a black hole. I'm unable to calculate the exact value, but the logical assumptions are valid. Thank you.